Write the following expression as a sum and/or difference of logarithms. Express powers as factors. So before we get started on this example, I want to take a minute to look at the properties that we'll be using to follow these instructions. So we have something called a product rule for logarithms, and the product rule for logarithms is when you have multiplication inside of a logarithm. And when you have that multiplication, you can do what we call expanding, which is to write the log of each one of those factors. Notice that the base of the original is base b, and the base of these two new logs are also base b. Then we have something called the quotient rule for logarithms, and that's where you have a fraction or division inside the logarithm. And in that case, you can write this as the difference of these two logarithms. The value in the numerator, expression in the numerator, will be the positive log, and the value or expression from the denominator will be the negative log. And then finally, we have something called the power rule. And the power rule for logarithms is when we have an expression with a power inside of our logarithm. In that case, the exponent is multiplied by the logarithm to rewrite it. So for our example, we have natural log of x minus 2 over e to the 3x. So because we have a fraction or division inside the log, we're going to start off using the quotient rule. So using the quotient rule, we would have natural log of the numerator minus natural log of the denominator. Natural log of x minus 2, we're going to leave in that format. It's as simple as we're going to get it, because it doesn't have a product, a quotient, or a power inside that logarithm. For natural log e to the 3x, we have a power, so we can use the power rule, and we're going to take that exponent or power and multiply it by the log. And then the last thing that we're going to be able to do for this expression is to simplify natural log e. Natural log of e is 1, and so our expression, our final answer, will be natural log of x minus 2 minus 3x. This question says, write the expression as a single logarithm. Before we work this example out, I want to focus on the properties that we're going to use for this example. So we have the product rule, the quotient rule, and the power rule. And the product rule is when we have a product or something multiplied inside the logarithm. The quotient rule is when we have division inside the logarithm. And the power rule is when we have a power inside the logarithm. So when we have a product, we can write it as the sum. When we have the quotient, we can write it as the difference. And when we have a power, we can multiply the log by that power. So when we start with a single logarithm and write it with multiple logarithms, we call that expanding. But our example is going the other way. We're starting with multiple logarithms, and we want to write as a single logarithm. So we're actually going to start with the properties that we see on the right and condense to what we have on the left. So we're starting with multiple logs, added or subtracted, and we're condensing to a single log. When we have a number multiplied onto a log, we're going to get rid of that number in the front by moving it to the power. So let's take a look at this example. We have log base 4 of x squared minus 36 minus 4 log base 4 of x plus 6. So we're going to start with any number that is the coefficient on the log or multiplied by that log. So that 4 is 4 times log base 4, or the coefficient of that log. We're going to use the power rule to move that into the exponent. So we would have log base 4 of x squared minus 36 minus log base 4 of x plus 6. We've got to do that property first, because if you'll notice that the other two properties, the product rule and the quotient rule, they don't have any coefficients on the logs when you condense them. So there's no coefficient or no number multiplied on our property here when we condense it. So we have to have no coefficients on those logs before we condense to a single log. So now I notice that I have subtraction. So with subtraction, we're going to use the quotient rule. The other thing you need to check for is to make sure that they have the same base, because you can't condense them unless they have the same base. So because we have subtraction, we're going to condense with the quotient rule. So we'd have x squared minus 36 in the numerator. X squared minus 36 goes in the numerator because this log is positive. And then x plus 6 will go in the denominator because this log is negative. And then finally, we want to simplify if we can. In this example, we have x squared plus 36 in the numerator, which is a difference of squares. That's x plus 6 times x minus 6. Our denominator is x plus 6, so we have a common factor that's going to cancel out. And that would leave us with log base 4 of x minus 6. In this example, we want to solve the exponential equation. And it says express irrational solutions in exact form and as the decimal rounded to 3 places. So before we start on this example, I just thought we'd take a minute to look at the different methods that we have for solving exponential equations. The first one is relating the bases, or it's sometimes called the one-to-one property. You can use this method whenever you can write your equation with the same base on both sides of the equation. In our example, we have a base of 6 and a base of 5. We're not able to write those two sides of the equation with the same base, so we're not going to be using the relating the bases method for this example. Then the other two methods are convert the exponential equation to a logarithmic equation. So that's when you are going to rewrite your exponential expression as a log expression. Excuse me, I should have said equation. Your exponential equation as a log equation. And we can do that with this example. And then the other method is to take the log of both sides. So if you have your exponential equation, you can take the log of both sides. I like to use natural log. Once you take the natural log of both sides, that introduces your properties of logarithms. And one of the properties that we can use here is the power rule to take this variable out of the exponent. And then once it's out of the exponent, we can get that variable by itself by dividing both sides by natural log of b. And we're able to solve for that value of x. So I'll show you the converting to an exponential equation method, and then I'll go through the taking the log of both sides method. So first I'll show you solving this equation by converting. So to convert this to a log equation, I'm going to write the word log, and I'm going to use the base of the exponent as the base of the log. Now this is a unique example in that we have two bases. You have a base of 6 and a base of 5. You can choose which of those you'd like to use. So I'll use the base of 5. So we have a base of 5. The log always equals the exponent. That's going to be x. And then what's inside the log is the other side of the equation, which is the 6 to the 1 minus 7x. Now from here, we have quite a bit of solving to do still. We're going to use the power rule to bring this power out of the exponent. We need to do that because that exponent has a variable in it. So that would be 1 minus 7x times log base 5 of 6 equals x. Then I'm going to use the distributive property. And I'm distributing this log base 5 of 6 to both of these terms. So that would be log base 5 of 6 minus 7x log base 5 of 6 equals x. Now I have two terms with x in it in this equation. I want to move all the terms with x to the same side of the equation. So I'm going to add this 7x log base 5 of 6 to both sides so that I can get those variables on the same side. That's going to cancel out on the left, leaving me with log base 5 of 6 equals x plus 7x log base 5 of 6. From there, I'm going to factor out the x. When I factor out the x, I'm left with 1 plus 7 log base 5 of 6. And now I can get that x by itself by dividing by what's in the parentheses, 1 plus 7 log base 5 of 6. I'm going to do the same thing onto the other side. That cancels out what's next to x, and now I'm left with my solution. X equals log base 5 of 6 over 1 plus 7 log base 5 of 6. Let me get my calculator and we'll type that in to get the decimal approximation. What I have here is the exact value. So I'll type that in my calculator. I need to go into the Math menu. The bottom of the list has a log base function where I can specify base 5 of 6. That's my numerator, and in the denominator, because I have multiple terms, I need to put parentheses, 1 plus 7 log, once again I need to get that special log from the Math menu, because that allows me to specify the base, log base 5 of 6, and closing parenthesis for the log and closing parenthesis for the denominator, and we get our decimal approximation. And I believe it said 3 decimal places. That's 0.127 if we round it to that third decimal place. Now some of you may not have a calculator that allows you to put the specific base in. Some of you may only have the buttons on the home screen, log, which is base 10, and natural log, which is base e. So if that's the case, then you would need to convert your log base 5 to one of those bases so that you could type it in the calculator. So I'll convert this to natural log, and this is what it would look like. Natural log of 6 over natural log 5, that's for the log in the numerator, and 1 plus 7 times natural log 6 over natural log 5. So this is what I would need to type in, and I'm putting parentheses in all the places I'll put it in when I type in the calculator. So in the numerator, I have natural log 6 divided by natural log 5, and that's my whole numerator. Then I'm going to divide, open parentheses for the denominator, and I have 1 plus 7, do parentheses, natural log 6, close parentheses, divided by natural log 5, close parentheses. Now I'm closing parentheses for the log part, closing parentheses for the denominator part, and hit enter, and you can see we get the same approximation, 1.27. Now I'll work that same example with the method of taking the log of both sides. So I'll take the natural log on the left and the natural log on the right. This is something we're allowed to do because log functions are one-to-one. So taking the log of both sides gives you an equivalent equation. And once we introduce the logs, we now can use the properties of logs, and the one we're going to use is the power rule. And we're using the power rule because that allows us to take the expression in the power out of the exponent. We want that variable out of the exponent so we can solve for it. So with the power rule, we get 1 minus 7x natural log 6, x natural log 5. I'll use the distributive property on this part to distribute the natural log of 6 to each term. That would give me natural log 6 minus 7x natural log 6 equals x natural log 5. And now I notice I've got variables in multiple terms. I want to move those terms with the variables to the same side. So I'm adding 7x natural log 6 onto both sides of the equation. It'll cancel out on the left side, leaving the left side only with natural log 6. On the right side, we have x natural log 5 plus 7x natural log 6. Then I'll factor out the x that these two terms have in common, leaving me with natural log 5 plus 7 natural log 6. The other side I'm just carrying down. And now I can get the x by itself on one side by dividing both sides by what's in the parenthesis. Doing the same thing on the left. That'll cancel out on the right, and I'll have my solution. X equals natural log 6 over natural log 5 plus 7 natural log 6. So this is the exact value. And I'll use the calculator to get that decimal approximation. So I can use the natural log button on the home screen of my calculator. Natural log 6 divided by, I need parentheses around the whole denominator. So that's natural log 5 plus 7 natural log 6. And I'll close parentheses for the denominator. And you can see we got the same value from before, 0.127. This question says solve the following exponential equation, express irrational solutions in exact form and as a decimal rounded to 3 decimal places. This equation is 6 to the 2x plus 6 to the x minus 12 equals 0. In this exponential equation, it follows a special pattern, and we're going to use a special method to solve this equation. What we're going to do is, well, what we should notice first is the special pattern. So the special pattern is that this kind of follows a quadratic format where we have 3 terms. Let me remind you, quadratic format. It's ax squared plus bx plus c equals 0. So quadratic equation would follow this form. And so the similarities to this format is that you notice we have our 3 terms, 6 to the 2x, 6 to the x, and the minus 12. So the minus 12 is like the constant. And then for the exponents, what we notice is that we have for the quadratic a 2 and a 1 for the powers. And what we have here is a 2x and an x for our powers. So because it follows that pattern of having the 3 terms, one of them being a constant, and also having one power be double the other power, we can use this special method, which is called U substitution. So with U substitution, we're going to let U be equal to the 6x that we see in the middle. And then if we were to square the left-hand side, so U is on the left, we're squaring the left, and I'm also going to square the right. What that gives me is 6 to the 2x. We get that by using the power rule for exponents. The power rule for exponents is when you have a power to a power, you multiply those powers together. So with this substitution, we're going to change our equation, which had those similar properties to a quadratic, and watch what happens when we make that substitution. So the 6 to the 2x becomes u squared. The 6 to the x becomes u. We carry down the minus 12, and that transformation that happened when we did the substitution turned the equation into a quadratic. So remember I said it started out similar to a quadratic, and when we did that substitution it actually turned it into a quadratic. Now this is nice because once you have a quadratic equation, you're able to use all of the methods for solving quadratic equations. This one is going to work out nicely by just factoring, but if you prefer, you could use the quadratic formula. So this factors into u and u. 4 and 3, we're going to have a positive on the 4 and a negative on the 3. And we'll set each factor equal to 0 and solve. So we can subtract 4 on both sides to get u equals negative 4. Add 3 on both sides to get u equals 3. Now we've solved this intermediate equation for u, but what we really wanted to know is what is x. So now we're going to bring back the substitution that we made so that we can bring back the x. So u was 6 to the x, so we're going to put this u to be 6 to the x, and this u to be 6 to the x, and solve these exponential equations that we have left. Now the exponential equation 6 to the x equals negative 4 is something that doesn't make sense because you have a positive value raised to a power equal to a negative value, and that can't happen. So we're not going to get any solutions from that equation there. But the other one we can solve by either taking the log of both sides or converting it to a logarithm. I'll take the log of both sides. If I take the log on the left, I have natural log of 6 to the x, and on the right, I'll have natural log 3. Then I can use the power rule to get that variable out of the exponent, and then I can get, I wrote 6 instead of 3. So then I can get that variable by itself by dividing by natural log of 6 on both sides, and that gives me my solution of x equals natural log 3 over natural log 6. This question says, solve the following logarithmic equation. Before we solve this example, I wanted to take a moment to look at a few of the methods for solving logarithmic equations. One method for solving is to convert to an exponential. So you would start off with a logarithmic equation, rewrite it in its equivalent exponential form. The other method is to use the one-to-one property of logarithms. To use the one-to-one property of logarithms, you have to have log base b on one side of the equation and log base b on the other side. So you have to have log with the same base on each side of the equation, and then you can say what's inside those logs are equal to each other. So in this example, we look at our equation and it has log base 6 of x plus 5 equals log base 6 of 6. So we do have the same base on both sides of the equation. So it looks like the one-to-one property, or sometimes this is called the property of equality, is the way to go. So because I have log base 6 on the left and log base 6 on the right, the one-to-one property says what's inside those logs have to be equal to each other. So this creates a linear equation that I can solve by getting x by itself. I'll subtract 5 on both sides, and that gives me x equals 1. Now, logarithms have a restricted domain. You can only substitute positive values into a log. So I need to check to make sure that I didn't come up with any solutions that cause that. So x can be negative, but the expression inside the log can't be negative. So I'm going to plug that 1 into my log. Log base 6 of 1 plus 5 equals log base 6 of 6. And because that expression inside the log comes out to be a positive value, I'm going to keep my solution of x equals 1.